So welcome back. We're going to continue our discussion of radial quantization today and use the general structure of what we find to introduce something called the operator product expansion for the stress energy tensor of a conformal field theory. This is the main structural, algebraic, structural device that we have in conformal field theory, and using it we introduce later something known as the Virasoro algebra. So we'll spend quite a bit of time explaining the details of this OPE, what it means and where you get it from. So if you recall, we were focused in the previous lecture what we're interested in here is building quantum theories which are conformal field theories. So I'll put a Q there to indicate that it's a quantum conformal field theory. And our main tool is the path integral. Which, for a variety of reasons, I will do in Euclidean space. And I've elaborated on those reasons in the previous lectures. And using the path integral, we can write down the prescription for a quantum correlation function of n fields, the time-ordered correlation function of n fields you can find via a limit of a path integral expression that looks something like this. Okay, that's something that comes from the Advanced Quantum Field Theory course. In that course we had an extra I in here, and we did everything in Minkowski spacetime, but if you just replace every instance of t with minus I beta, then you, in the derivation of the path integral, then you will conclude that this is a valid expression for the time-ordered correlation function. Now, the word radial in radial quantization refers to a specific choice of coordinate system. So here this is time, but of course we're doing things in imaginary time at the moment. So this time ordering symbol here pertains to beta, right? But because our system is invariant under rotations, we're somewhat free in what coordinates in what we define as a time coordinate and what we define as a space coordinate. So Euclidean space-time looks like this, x beta if you like, and it's rotation invariant. If you have a Minkowski or Lorentz invariant action, then this action is rotation invariant under this imaginary time rotation. I gave a small example of that last lecture. So the choice of which axis is time is pretty arbitrary, right? Because you can just do a rotation and you're doing the integral along another direction. So the choice of which axis you call time is somewhat arbitrary. Why not choose the x-axis as time, or the beta-axis, or x plus beta, or x minus beta, or any number of things, any manner of such things. Further, if your action is conformally invariant, under the Euclidean conformal symmetries, as these ones turn out to be, right, then why even focus on, you don't even have to fix your attention on axes which are straight lines. You could use even more elaborate coordinate systems. And there's one particular elaborate coordinate system that we're going to focus on today, and that's the polar coordinate system. So polar coordinates, why not, right? You can use polar coordinates, you can use elliptic coordinates, you can use whatever oblate spheroidal coordinate systems. Whatever coordinate system makes you happy, you can use. And for reasons that I explained several lectures ago, we're going to use polar coordinates because it gives a kind of direct connection between quantum systems on a circle and partition functions on the plane. So I'll explain it in one moment. So we have the radial coordinate and we have the angular coordinate as well. So every point has a radius and an angle. We won't speak so much about the angle coordinate. We will in fact focus mostly on the radial coordinate, because the radial coordinate is the one that will give the interpretation of time. Right? It's still arbitrary what we call time. So the radial coordinate is to be our time-like coordinate in this path integral representation. And perhaps you recall several lectures ago I drew these circles, and you think of this as being under a conformal map equivalent to a system which is a circle and with time running up. So there's multiple interpretations for the same path integral depending on what you want to call time. If you want to call time the y-axis, then you are talking about the thermodynamics of an infinite one-dimensional system. If you want to call by time the radial coordinate, then you're thinking about the thermodynamics of a quantum system on a circle. The choice of what you call time and space will each time lead to a different notion of time ordering. So this is just a and it also leads to a different ward identity. You get a different ward identity for every different choice of what time is. And ultimately, you end up with a different Hilbert space realization. A different Hilbert space realization of what these correlation functions are referring to. So it's just like saying there's more than one way to get a correlation function defined on Euclidean spacetime. So there's a variety of reasons why you might want to think about quantum systems on circles rather than quantum systems on the infinite line. One of them is that there's no infrared divergence issues that you have to worry about. Not worry about infrared problems, and also sort of arguably circles are much more physical than infinite lines. You can imagine building quantum systems on circles in a laboratory. There's lots of mathematical reasons why circles are more interesting than the line, to do with the diffeomorphism group of the circle. I won't comment any more on these issues. So for these reasons, we're going to focus on quantum systems defined on circles. And we're going to declare the polar coordinate, radial coordinate r as our time coordinate and theta as the space coordinate. And locally, this is just a choice. And that means that whenever we have a time ordering symbol, t, we have to take these observables, which are located at various points in space-time, and this path integral here is then regarded as giving us a correlation function where these fields are ordered in increasing radius. So I'll draw one more picture for that. So to differentiate the time ordering symbol for when we're using the radial coordinate versus when we're using the y coordinate, I'm going to just use a different symbol so it's sort of clear from the context of the symbol what ordering we're using. So I'm going to introduce the radial ordering symbol. How does it work? Well, if you have two quantum operators, a hat and b hat, and we're using complex coordinates here, then the radial ordering symbol says that AZ comes before BW if Z is bigger than W. The radius of the Z coordinate is bigger than the radius of the W coordinate, and vice versa if it's the other way around. So this is radial ordering. So when we choose that coordinate system and we do our path integrals that way, then all our correlation functions are with respect to radial ordering. And so you're going to see expressions like the following. So whenever I write something like T, Z, A, W, this actually means the radial ordering of T, Z with respect to the vacuum. And as we go through the course, we're going to acquire the very irritating habit of conformal field theory papers and texts of not even writing the expectation value symbols. I'll do this a bit later. This is particularly distracting but you just have to get used to it. It's because it's universal notation. I'll introduce that presently. Before then, though, we have to make sense of something. So we're going to try and make sense of an equal time, but we don't mean time anymore, we mean equal radius, commutators. That's things that will appear. Certainly they appear in the ward identities and are the crucial tool for actually finding generators of symmetries. So we're going to have to make sense of these in this radial coordinate system. And, well, there's one way to make sense of them. You just write down the commutator, right? But there's a very useful device, since we have a complex coordinate system that we can make reference to, z's and w's, then it turns out there's a really neat way to use contour integrals to implement equal time commutators. So we've previously encountered situations where we've had an integral of 1/2 of the ward identity over an equal time slice. So that's how we find conserved charges, right? You integrate over an equal time slice. Sorry. That's the exact opposite of equal time slice. You integrate over space, right, of something, and that gives you the conserved charge from a conserved current. So we've encountered these kind of things. In the radial coordinate system, these kind of integrals, the integral over all of space for at a given time, they look different, right? They look like the integral over all angles for a given radius. So here's the spatial coordinate is the one that is the angular coordinate, and the integral over all space is actually a closed integral around a circle. So this becomes the integral around a closed contour of something. Now, it's impossible to resist the temptation of doing contour integrals when you see something like this. It's exactly what we're going to do, in the hope and that things will become nice. And what do these somethings look like? Well, the somethings are always products of operators at various points. So we want to understand how to do these kind of integrals here. Well, we have understood. It's just a contour integral. Just integrate around a circle. And an equal time commutator, I'm going to show you a neat trick for how to get an equal time commutator via contour integrals. So suppose here's our plane. Now we're using complex coordinates. Okay, I'll call this W. Put primes on it. Now we want to integrate around a circle. We want to find out how to build a commutator of these two fields using contour integrals. An equal time commutator. That's something that occurs when we want to build the generators of symmetries. Now, how can we do that using an expression like this? Well, one way of doing it is you integrate around a circle just below W. Call this contour C1. And then you subtract from it the integral around just outside of W. Sorry. So the objective is to build a conserved charge, which you do by integrating over space of something appearing in a conserved current. And that is now a contour integral. And then to somehow use contour integrals to then build a commutator, an equal time commutator. And the way we can do that is exploiting this fact here that we can integrate A over the contour C1. Actually, do I want it that way? Yes, I do. Just epsilon away from the point where the second field operator appears. And that'll give us the operator A in radial ordering just below or to the left, to the right. To the left. Hang on. Now I'm confused. So A, in radial ordering, A goes to the left if Z has a bigger radius. Okay, so that we'll get from this term here. So if we integrate A around contour C2, which is just epsilon to the other side of W, we're going to get something where we have an AB. And if we subtract from that the integral around a contour just inside W, we're going to get BA after radial ordering. And that suggests, and so I'll write that out in a second, but if you look at that, you can see that this contour integral here is actually the same as doing a tiny little contour integral around the circle there. I'll draw that again in one moment. As long as everything is sufficiently holomorphic and nice. probably quicker just to write it than it is to say it. I use the other direction here as the question. I don't think so, no. So here C1 goes this way, and C2 goes that way, which is the same as minus going.
But in your picture there, you go both in the
Yeah, but there's a minus sign here.
Oh, sorry.
Yeah. So I'm orienting the contours so that if you have a contour going this way, it's equal to minus the contour going that way. So this is the reason these two sides are equal. I haven't actually proven that yet. This is, I'll put the explanation now, because the reason that integral equals that commutator is because this commutator is given by two contour integrals there. And yeah, now I have to tell you that I'm doing everything under with respect to radial ordering. So this is something you just have to get used to. An expression such as what I've written up there is not making sense formally as written. These operators are naked. They have no expectation value signs around them. Such naked expressions are forbidden We refuse to interpret what they mean. Instead, whenever you see such an expression, you have to do the following translation. Whenever you see something like a product of operators, some equation involving a product of operators, something blah 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 equals whatever d hat e hat whenever you have equations involving objects with hats, you must interpret them only after taking radial ordering So this is a crucial clarification that we have to make whenever you see an expression involving hatted quantities. Actually, it's even somewhat worse in the literature than this. You'll often see such quantities written down without hats. I've made an effort to put hats on whenever something is quantum in this course, but your standard literature sources won't bother with the hats. You'll have to know from context that we're talking about a quantum quantity or a classical quantity. So this is a critical thing to be aware of now. Anytime I'm writing things like this, equations involving operators, this is only valid once you apply radial ordering and expectations with respect to zero. They're not meant to be valid in generality. Now this change of notation, I mean, because that's all it is, right? I've just used some fancy schmancy complex analysis to write down stuff you already know. Why bother? Well, because it helps us in two ways. One is we can express things that were previously complicated in a less complicated way, so it reduces the surface area of things you have to memorize, which is always a good thing. However, it also, wrong one, allows us to deduce new results, new identities, which otherwise would be difficult to express, or even discover. So probably the most important identity that we can now extract is the commutator of a primary field with a stress energy tensor. This is the most critical quantity pretty much in conformal field theory. Because it's what allows us to deduce so much structural information on the fields of a conformal field theory. All right. I think I'm using capital phi. Yes, I am. So let phi hat WW bar be a primary field. So primary fields have this nice transformation behavior in correlation functions under conformal transformations. And what we can do is write the transformation of a primary field in terms of complex coordinates and exploiting this identity here. We get something quite nice. So if you vary a primary field with respect to some infinitesimal conformal transformation, so these E's must obey the that equation that specifies them as an infinitesimal conformal transformation, then you can express that variation in a rather nice way. This we saw in the previous lecture. This is this discussion of Gauss's theorem in complex coordinates. Led to this. So this is the conformal Ward identity. That's the conformal Ward identity. Okay, that's what we had in the previous lecture. But now we're going to use this contour integral trick to be able to write this as a commutator. So note that now we're writing our Ward identities with respect to radial ordering. In the previous lecture we did it with respect to Y ordering, but every choice of time coordinate gives you a different Ward identity. Yep.
The first radial ordering symbol is...
Oh, the first radial ordering symbol is wrong. Now it's right. I could put in another integral in there. So we've exploited this trick. And we've arrived at the following commutator expression for the conformal Ward identity.
I'm sorry. I'm not quite sure if this is right, but in the last lecture we had a minus sign in one of these terms.
Oh, so the question was we had a minus sign in one of these terms.
And the conjugated term, there was a minus sign.
Yes.
Where it doesn't.
Just check. So did we? Yes, indeed, we had a minus sign.
And also there was the difference in the integration. The conjugated t, you have to integrate over the not conjugated z.
Z bar, Z bar. Now I am seeing the same thing too. What's the explanation? Let's see. So the minus sign we fix with the contour, but the integral over the not conjugated z is different. I think there must have been a mistake in the previous lecture. Now that I look at it, that doesn't look right anyway.
And the next question is, do the second epsilon has to be conjugated or?
Yeah, yeah. So epsilon z bar. So I'll write out the equation what we had in the previous lecture, and then I'll see if we can't find the connection. Because as I look at the one from the previous lecture, it doesn't look quite right. So I wonder if there was a mistake there. Okay, so in the previous lecture, we had the expression So we had the expression d epsilon comma epsilon bar x hat, but x hat is just a product of field operators, so you can apply it more specifically to just one field operator, which is what we're meant to be doing here. And what I wrote down in the previous lecture was 1/2 I integral around C of minus dz, and the next bit looked like this. So that's what I have written down in my notes.
And we have corrected it last time. So
We corrected it last time so that this one had a z bar too, didn't we?
Yeah.
And then I had somewhere defined what t of z is. Yeah, here it is. So t of z is defined to be minus 2 pi t lower tzz, and t bar hat z bar I think the answer is when we raise and lower the indices.
I think there's a mistake that you integrate over the wrong contours. If you switch the dz and dz bar,
Then everything's fine, I agree. But I'm a bit wary of saying, so the proposal is that I just integrated over the wrong variables here, that this should be a z bar and this should be a z. I'm aware, and it's very tempting to admit that that may be the mistake, but I'm just cautious for the moment because I wonder if it's also the metric is playing a role as well. So use Gauss theorem. Because the Gauss theorem that I quoted to you definitely had this order of z's and z bars. I think the answer is in the metric. So we've got upstairs indices here. And if we apply the metric to get downstairs indices, this will turn z bars to z's and z bar to z. Because the metric in complex coordinates is not the one you think it is, right? So the metric is with respect to z's and z bars, flips z's to z bars. So I do think they're equivalent when you change upstairs indices down to downstairs indices. And you have to change the epsilons up to ups as well. So I do believe they're actually the same. I will So this I won't. So the claim is that this water identity is the same as that one when we use the metric to raise and lower the indices. Now I don't want to do that calculation right now because I'm somewhat convinced I'll make a mistake. So I will confirm that and tell you if it's false next week. But if it's true, then I probably won't mention it again.
Then we need to have a bar and the second epsilon.
Yeah, so the second epsilon there needs a bar. You're right, thank you.
Line above, there's a bar missing in the T bar Z bar.
Yep. Oh, sorry. Oh, there's bars missing everywhere. Yeah, thank you. So yeah, the claim is that this is equal to that. Just to be clear what the claim is. And I think that's not false. And I have one point where I can check this. Yeah, it is actually, I do believe this is correct now. I found an expression for the metric G. I'll write it slightly differently. Remember that this equals a half, but that equals 0. So when you use the metric to lower and raise indices, you flip from Z's to Z bars. Okay, well, good that came to discussion. So this course is based upon several references, but luckily the notation is much more coherent than in other parts of quantum field theory. And largely everything agrees between the different sources. People don't choose different metrics. I was concerned for a moment that the difference here may have been due to a different choice of reference, but I think they're the same. All right, well, taking this as our expression of the conformal water identity, we can realize it as this particular commutator expression there. And that allows us to introduce the conserved charge corresponding to the symmetry of a conformal transformation, Q of Z. And it's, well, you look at that expression and you can see already what it must be. I'll subscript it with maybe epsilon bar.
Sorry,
Yep.
but shouldn't it not depend on Z after the integral?
Oh, should it not depend on Z? Yeah, that's actually a good point. Yeah. The question is, well, should it not depend on Z? Yeah. Once you've integrated Z out, it better not be there anymore. So this is the conserved charge corresponding to the conformal symmetry. Z goes to Z plus epsilon. Now, there's something really rather nice that we know about primary fields. So we know by definition, right? That's the beauty of primary field definition, is it's a definition, you don't have to prove it. That a primary field under such a conformal transformation like this goes to, I'll make the ZZ bar. So that's what it means to be a primary field. A primary field is an operator which transforms in that particular way there. Now for this to work, because on the left-hand side, we now know how that thing transforms, we just use that formula. And on the right-hand side, we have this expression in terms of this conserved charge. For that to work, t and phi must behave in a certain way when you take their commutators. So using this formula here, for f of z equals z plus epsilon, will allow us to work out what the transformation of a primary field is. We just use that formula to work it out. And what you get is that this equals star This is just a matter of inserting this particular function f into that expression there and taking a Taylor series to first order in epsilon. Of course, you get higher order terms, but they're not really important. Now if we substitute that into the conformal ward identity, then we're going to end up with a particular constraint on how phi and t behave when they get close to each other. So this is something that has to be true, and when we put it in the conformal ward identity, the left-hand side has to equal the right-hand side. But that can only be the case if, when you take the radial ordering of t hat z, so we have this really striking result that as tz, the behavior of tz and phi w as a function of z minus w has to be like this. The only way it can work is if this radial ordered term behaves like that, because when you do the contour integral, you won't get the right answer unless it does. So really forced to conclude this here. And there's a corresponding anti-holomorphic version. Which is just exactly the same, but with bars everywhere.
I quite sure that it has to be twice the 1 over z minus omega square, and not without square.
This one here, oh, one of them is wrong. Oh, goodness. Yeah, I think they're both got ones. I don't know why I wrote squareds there. Let me just double check. Oh, other way around. Sorry. So nice to write squareds, but this is really not squared. So I'm going to rewrite this fundamental expression here. This is the conformal ward identity what it means for the stress energy tensor and a primary field. Now, it's not so surprising, given that what we already know about correlation functions of conformal field theories. We know that if you have two primary fields, the correlation functions are constrained in a certain way. And so this sort of restriction on how these correlation functions can behave as z goes to w isn't entirely surprising. But what's new here, the new content, is that we have a new field, Tz, which is not necessarily primary. We don't know very much about Tz at this point. We know it's a field, and we know that when you bring that field close to another one, then the correlators have to behave in that peculiar way here, which is not quite the same as a primary field. Tz looks like a primary field. Turns out it isn't, which is actually one of the most important consequences of this discussion. We're going to rewrite these identities using a symbol, twiddle. And twiddle means equal up to holomorphic or regular expressions under radial ordering and expectation values. Okay, so that's what the symbol twiddle means. The symbol means the left side and the right side are equal up to expressions which are regular as z tends to w, and only when you take radial ordering and expectation values. So in that way, when you use that notation, you can rewrite this conformal Ward identity as follows. So it's a bit easier to write down, but that's only because you defined a lot of the information in that equation in terms of a symbol. So this expression here tells us about the short distance behavior of Tz and phi w as you bring them close together. So it says that the fluctuations, the quantum fluctuations start to diverge as 1 over z minus w squared as you bring these two operators close together. And there are additional terms, there'd be infinitely many regular expressions, holomorphic regular functions here, but as you bring z to w, a holomorphic function will just tend to a number. So this is true up to some kind of constant at z equals w. Now there's a special name for such expressions that tell you about the behavior of quantum fields when you bring two of them close to each other. Such expressions are called operator product expansions, introduced by Wilson. Studied in the context of quantum chromodynamics, but actually they find their widest range of applications in conformal field theory for the moment. Okay, what do we have? So this star here, this neat looking identity, tells us the short distance behavior as you bring a product of fields together in terms of, well, a list of fields at one location, not two locations now, but just one, namely W, multiplied by some possibly singular complex functions. So you can take products of fields and replace them with sums of fields at a single location, as long as you bring Z close to W. That's like an algebra, right? In an algebra, you take two things, you multiply them, and you get a list of just things back in the algebra again. And that's not just a superficial resemblance. We're going to exploit the operator product expansion to build an algebra later on. And so this particular expression here, star is the OPE of T and phi. We're going to see plenty more OPEs before we're done. And we're going to observe some general features of OPEs. And these general features will allow us to introduce an algebra, a Lie algebra, called the Virasoro algebra. This will correspond to what happens when you take the stress-energy tensor to generate one conformal transformation product followed by another in the quantum setting. So the most general, what does an OPE look like in general? Well, if you have two fields, one at Z, one at W, then in expectation, radial ordering, blah, 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 all those things, this has to look like a sum, a single sum of terms of the form of fields at location, just at location W, multiplied by possibly singular complex functions, Z minus W. So this is just a notation for a list of field-like objects, and the only requirement is that at W they're non-singular in expectation and radial ordering. So remember, everything is up to this twiddle sign here. And so, for example, for the case that we've been looking at, star star, what's the composite field 1, t hat phi hat 1? Well, that is none other than the coefficient of the term z minus w. And if we look down here, that's dw of phi. So we call that a composite or secondary field, descendant field. You take your original field, you differentiate it with respect to the argument w, you get something else that's local and will actually be non-singular at the point z. All right. Yeah, that's pretty much all I want to say today. So we've used the conformal ward identity to derive a constraint, if you like, on the behavior of fields as they go, as their arguments tend to each other, in the case where one of the fields is a stress energy tensor field and the other is some primary field. And that allowed us to write out this operator product expansion T for T and phi. It has a very particular form. In the next lecture, we're going to take the first and probably only example that we're going to take in this course. We're going to solve the free boson without mass, the massless free boson. And we're going to identify in our solution, it's a complete solution, we know everything about that system. We're going to work out what are the primary fields of that system. What does the stress energy tensor look like in terms of the Lagrangian, and then hence what's its operator expression. We're going to work out the operator product expansion of the fields with themselves. And then we're going to discover something quite remarkable when we take the operator product expansion of Tz with itself, Tw. And that will lead us to the last part of this course, which will be introducing this thing called the Virasoro algebra. But for now, I'll stop here. Thank you.